Welcome to the third video in this series. In this video, we'll be discussing scientific notation, metric prefixes, exact and inexact numbers, and precision and accuracy. In the sciences in general, and chemistry in particular, it is not uncommon to work with very large and very small numbers. In the previous video, we encountered two such values. One was the mole, which we defined as 602 billion trillion. The other was the liter, which we defined as 1/100th of a cubic meter. It would be very tedious if we had to write these out in full each time we dealt with one of these numbers. Therefore, we employ two shorthands, the use of scientific notation and the use of metric prefixes. Both of these topics are likely review for many. However, because of their importance, I will go through them briefly. In scientific notation, we multiply a number by 10 to the power of some value. So, for example, we could write 100 in scientific notation as 1 times 10 to the 2. Going back to the examples from the previous slide, we could write the value for the mole as 6.02 times 10 to the 23rd, or we could write the liter as 1 times 10 to the minus 3. Besides providing a compact way of writing large and small values, scientific notation also simplifies calculations, especially multiplication. For example, in multiplication, what we would do is we would multiply the pre-exponential values together and then add the exponents to achieve the final value. For example, with 5 times 10 to the 23 times 2 times 10 to the minus 5, we would first multiply together the pre-exponential terms, the 5 and the 2. This yields 10. We would then add together the exponential terms, 23 plus minus 5, arriving at times 10 to the 18. 10 times 10 to the 18 can be further simplified into 1 times 10 to the 19. The other compact notation we'll use is SI or metric prefixes. Most values that you will encounter will utilize these prefixes. However, it's important to know how to go between metric prefixes and scientific notation in order to do calculations. Several of the metric and SI prefixes are outlined in this table. Of these prefixes, the most important ones for you to know that you'll encounter frequently are highlighted in red. K times 10 to the 3 for kilo, M times 10 to the minus 3 for milli, and the Greek letter mu times 10 to the minus 6 for micro. Other values that you may encounter are outlined in blue: mega, deci, centi, nano, and pico. We're now going to work through a problem where we have to go between scientific notation and these metric prefixes. What we're going to do is we're going to multiply 15 grams together with 2.3 kilograms. We're then going to give an answer in the nearest appropriate metric prefix. The first thing we would do is we would convert 15 grams into 1.5 times 10 to the 1 grams. This brings 15 grams into a scientific notation. We would then convert 2.3 kilograms into 2.3 times 10 to the 3 grams. The next thing we would do is we would multiply these together, multiplying the pre-exponential terms and then adding the exponential terms. We would also multiply grams by grams to give us grams squared. This would yield 3.45 times 10 to the 4 grams squared. Converting this into the nearest metric prefix, we would take 10 to the 4, giving us kilograms, leaving us with 34.5. So the answer would be 34.5 kilograms squared. In the next video, we'll get into the fact that the reported answer that we would really give would be 35 kilograms squared. Now we will turn our attention to a seemingly simple topic, numbers. In the previous video, we talked about one part of a measured quantity, the unit. Now we'll talk about the other part of that measured quantity, the number or the magnitude that describes that measured quantity. All numbers can be broken down into exact and inexact numbers. The difference between an exact and an inexact number comes down to the certainty that one places on whether or not that value is the exact value that is being measured. An exact number is something you have absolute certainty of, either because it is a counting number or because it is something that you've defined as being exactly that number. For example, in this picture, we have exactly one duck staring at us with what is obviously evil intent. We can count the number of ducks in this picture, and we know for a fact that there is exactly one duck. We define the mole as the number of particles contained in 12 grams of carbon-12. Therefore, we know for a fact that 1 mole of carbon-12 has a mass of exactly 12 grams. In contrast, an inexact number has uncertainty attached to the value. Anything that one measures is inexact because there will always be uncertainty in that measurement. For example, the temperature recorded by this thermometer is 37.5 degrees Celsius. There's some uncertainty in that number, and that uncertainty is in that last digit, that 0.5 degrees Celsius. Sometimes counting numbers are inexact as well. This is especially true in population statistics. This school of fish contains approximately 1,500 fish, where there being uncertainty in the hundreds place. As you may have noticed, the number you report in an inexact number tells you a lot about the certainty you are placing on that number. We'll get into this in more detail in the next video when we talk about significant figures. The uncertainty in these values are inherently linked to two properties, accuracy and precision. Accuracy just refers to how close your measurement is to the true value, while precision refers to how close each individual measurement is to the other measurements. We can use the classic example of shooting at a target to illustrate accuracy and precision. If something is both accurate and precise, you'll have all of your bullet holes in the bullseye very closely grouped together. As you lose accuracy, you maintain that grouping, but it goes away from that bullseye. If you have something that's accurate and not precise, all of your bullet holes are grouped around the bullseye, but each bullet hole is far apart. When you have something that is not accurate and not precise, then the bullet holes are neither close to the bullseye, nor are they grouped tightly together. To science this up a bit, we're going to talk about accuracy and precision in terms of scales. If you have a well-calibrated scale, so a scale that can very accurately reproduce mass, and something that will give each value of mass close to what has been reported before for the same substance, you have a highly precise and an accurate balance. If that balance isn't calibrated, each measurement is going to be close together, but the value is going to be off from the true value. If you use a balance that's imprecise but it's been calibrated, then each value that you measure for the mass is going to be close to what the true value is, but each measurement is going to be off from the other. If you use a broken balance, then your measurements will not be close together, nor will they be close to the actual value of that mass. Let's see how these would relate to a real-life experiment. Let's say that we had to measure a mass. Depending on what precision we need in that measurement, we would choose between one of the two calibrated scales. We would only want to use a calibrated scale because they're accurate. We would use either a high precision scale if we need a very precise value, or the low precision scale if precision wasn't that important. In the high precision scale, we might get a value of 1.7631 grams, where that last digit containing the 1 tells us about our uncertainty. That's the uncertain value that we have in this measurement. On our low precision scale, we might measure a value of 1.8 grams, where that 0.8 gram digit is where our uncertainty is. Both of these are going to come up again when we start talking about significant figures. That brings us to the end of this video. Some of the key takeaways are that we work with numbers in terms of scientific notation or metric or SI prefixes. The important SI prefixes that we need to know are the kilo, the milli, and the micro. Some other important units that may come in handy are the mega, deci, centi, nano, and pico. Exact numbers are numbers whose values are known exactly. Inexact numbers, on the other hand, have some uncertainty on them. All measurements will yield inexact numbers. When reporting measured values, it is important to take into account accuracy and precision. This will become important when we start talking about significant figures in the next video. So, as I alluded to, the next video will cover significant figures and how to perform operations using them.